Okay, in this video, I'm going to be going over a test review that was given to me for my physics class. It's a Physics 2 class, and this covers material from chapters 21. Oh, if I can write it on here. 21 to 23 from, and I'll put it in the description, Giancoli Physics with Applications. And like I said, this was given to me by my physics teacher, so it will probably prove very helpful for you if you are studying these chapters to review these questions before a test. Okay, so let's just go ahead and get started. For number 1, we have here that a solenoid of 200 turns carrying a current of 2 amps has a length of 25 centimeters. What is the magnitude of the magnetic field at the center of the solenoid? So I believe this was from chapter 21. And let's go ahead and let's highlight what we're given here. So we're given that it's a solenoid of 200 turns, and it's carrying a current of 2 amps and has a length of 25 centimeters. And then we want to know what is the magnitude of the magnetic field at the center of the solenoid. Okay, I recommend that when you're taking your classes, you're writing down every single one of the formulas that you're given, because that's really going to come in handy here. So if we write down what we know, which is the solenoid has 200 turns. Well, if you remember from class, that's represented by N. So our N is 200, and that we're carrying a current, which is represented by I, of 2 amps. And our solenoid has a length, L, of 25 centimeters, which we have to have that in meters. So that's going to be 0.25 meters. And we want to know, our unknowns is what is the magnitude of the magnetic field at the center of the solenoid. Okay, well, we have an equation for this, and our equation is mu naught times N, or we can say, big N, times I, divided by L, gives us the B center of the solenoid. So all we have to do then is go ahead and sub in our values here. And that's going to be mu naught, remember, is just a constant. That is 4 pi times 10 to the minus 7. Okay, and then our N we have over there in our givens, that's 200. Our I is 2 amps. And what else did we have? Oh, we're dividing by the length, which is 0.25 meters. And then we can go ahead and solve for this. And when you put that into your calculator, you're going to get 0.002. And remember, Tesla's is what we use for the magnetic field. And this is just magnitude, which is already positive. So it's still 0.002 Teslas is the magnitude of the magnetic field at the center of the solenoid. So again, it just fell together really easily when we saw that we had an equation that we could use. Okay, so let's go now to this one. A loop of radius r equals 3 centimeters is placed parallel to the xy plane in a uniform magnetic field B equals 0.75 Teslas. The resistance of the loop is 18 ohms. Starting at t equals 0 seconds, the magnitude of the field decreases uniformly to B equals 0 Teslas in 0.15 seconds. What is the magnitude of the electric current produced in the loop during that time? Okay, so it seems like a lot, but one thing, let's go ahead and let's look at what we're given. So we're given that we have a loop, and the loop has a radius of r equals 3 centimeters. So we know that the shape here that we're talking about is going to be a circle, because a circle has a radius, right? So we're given that we have a circle loop, right? And our radius is 3 centimeters, which is 0.03 meters. Okay, and it's placed parallel to the XY plane in a uniform magnetic field of B equals 0.75 Teslas. Okay, so let's write that down. That we have our loop is parallel to B, which is 0.75 Teslas. Okay, and then we have that the resistance of our loop is R equals 18 ohms. So we have R equals 18 ohms. And then it says starting at T equals 0 seconds. Should have made that. Oh, goodness. Okay, starting at T equals 0 seconds, the magnitude of the field decreases uniformly to B equals 0 Teslas in 0.15 seconds. Okay, so then we're told that our change in time is going to be 0.15 seconds. So our initial time, time initial is 0. Time final, or you could even say T prime, is 0.15 seconds. So if you're doing a change in T, it's going to be what? Final minus initial, and final minus initial here is 0.15 seconds. That's what delta means, right? Delta means final minus initial. And it says the magnitude of the field decreases to B equals 0 Tesla. So we know that our change in B is going from final. What is our final? Our final is 0 Teslas, right? This is B final minus B initial. And B initial is 0.75 Teslas. And so that is going to tell us that our change in B is equal to negative 0.75 Teslas. Okay, in 15 seconds. Then it says, what is the magnitude? The magnitude of the electric current produced in the loop during that time. Okay, so we were given a lot of information. The thing that I have just realized while doing these problems is that when you're given this information, let's go ahead and write down our unknowns. And we want to know now the magnitude of I. You need to look, or I encourage you to look for the relationships between the things that you're given. Everything in life is about relationships, relationships to how you view yourself, how you view the world, and that corresponds to, so many things, and not just as far as our relationships of perception, but the relationships between, the people, the other organisms that we are interacting with. And so I've found, if that doesn't make sense to you, that's completely fine. But I found that looking at physics in the same way, that this is all about relationships. So what are we given here? We're given resistance, right? We're given resistance. We're given change in time. We're given that we have a loop of a circle that has this radius, and also that it's parallel. So if it's parallel, you're going to be talking about something that has to do with angle. So there's going to be some type of angular, perhaps, thing going on in here. And then you have, that your resistance. So that if we're talking resistance, we can remember that we have the equation. Oh, stars. Okay. The equation IR. Remember, IR equals voltage, which is also another way of saying EMF. And this is how you can start to get your equations, because equations are about relationships. Like, this is what this means. This means that the current and my resistance, they have a relationship, and that relationship it equals a voltage. And that's what this equal sign means. It's a relationship. It says this equals this. When this goes up, this goes up. It is a relationship. It's a correlation. And so it's very important to see these things as relationships and not just as alphabetical numbers on a page. I hope that maybe that resonates with you and it helps you a little bit. All right, so let's keep it going. And then we have change in time and things of that nature. Okay, so we're asked for magnitude of electric current. Well, we're told here about a flux in our magnetic field. We have a change in our magnetic field. And if you remember, we have an equation that talks about magnetic flux and that talks about the relationship of magnetic flux to EMF. And that would be really helpful here. So if we recall that EMF is equal to, now we're doing magnitude, negative N, which is, remember, how many loops of something and, whatever we're talking about, the change in magnetic flux over the change in time. Well, again, another way to write that is going to be negative N final minus initial over change in time. And how do we know what our magnetic flux is? Well, we know magnetic flux is B a cosine of theta, which is what? This angle is the angle between the magnetic field and the plane of the area. So let's write that down. This is the angle. Again, the relationship between the magnetic field and the plane of the area. So not just the area, but the plane of the area. And the plane is like the face of the area. And we're going to go over that in just a second. Okay, so if I look right here, I know that I have a loop. And I know that this area is, and it says that it's placed parallel, so to this magnetic field. So say I have a magnetic field that's going into the screen, right? Or hold on, let's do it like this. Could even do it like this. It's parallel. So if we see here that if we're looking at the angle between the B field and the area, now the plane of the area, so this is right here. So say I have, a good way of seeing this is if you were sitting on top of the face of the area, the way in which you were looking would be the way the plane of the area is facing. And since this guy is going this way, well, if they were perpendicular, this would be, so if they were like actually right on top of each other, it would be like this. And that would be 180. But we don't have that because instead we have this. Right? And so we have a 0 degrees. So this is going to be cosine of 0. So we now know, because there's no like angle between this, right? They're just going one way and going the other. So we have cosine parallel means, let's write that up here, that our theta equals 0. And cosine of 0 is 1. All right, so let's erase that. And then for our area, right here, well, we know we're dealing with a circle. And so our area is going to be pi r squared. A way that I remember that, because I always was seeming to get my different things mixed up, is that is this mnemonic. Cherry pies, delicious. Apple pies are too. Okay, so this is circumference, pi, d, right? And this one is A equals pi, r, this is r, and this is 2, pi r squared. And the way that I remember which one comes first, the C or the A, is that I can't have area if I don't have the circle, if I don't have the circumference first. So you have to have this part before you can have this part. So before you can have an area, you have to have a circumference. So that's how I remember which one comes first. Maybe that's helpful for somebody. Let's erase that. Okay. All right, so now we have our area. Now what about our magnetic flux? Because this is what we're looking at filling in right here, so we want to use this equation. So we have that this is BA cosine theta. Well, we know that if we go over here, our B field is the thing that is changing because we have a change in B, we figured out was final, which was 0 Teslas, minus the initial of 0.75 T gives us negative 0.75 T. So we can actually fill this all in now. And come over here. We can say that this equals negative n, well, it's just 1, right? Because it says a loop. So it doesn't say 2 loops or, it's just 1. Negative 1. And this is a magnitude, so you could leave the negatives out. But I'm just going to leave it in so we can see something at the end. The change in B was negative 0.75 Teslas times A, which is pi. That doesn't change. There's nothing about the area here that's changing. Pi times 0.03 squared times cosine of 0 all over the change in time, which we found was 0.15 seconds. That was actually given to us. All right, so let's put this in our calculator. Okay, and so I get that this equals a positive, but either way we're doing magnitude, of 0.0141371666941. This is going to be volts, remember, because this is our EMF. That's the equation that we are looking at the relationship between all of these things with. But we don't want EMF, but we know that EMF equals, right here, the same as current times resistance. So if we take this and divide it by our resistance of 18 ohms, we will have our current. So let's go ahead and do that. And we will get that our current is 0.0785398.163 amps, which is going to be, let's say, to 2 sig figs. Oh, whoops, one more zero, sorry. 1. Okay, so I get that that is I equals 7.9 times 10 to the negative 4 amps. Now you notice that this current is positive. This is something your teacher may ask you. So we see here that the magnitude of the field is decreasing uniformly. Well, this guy right here, he wants everything to stay the same. So if around him is decreasing, that's going to produce a current in him, because all you need is a changing magnetic field, doesn't matter if it's increasing or decreasing, to induce a current. And then a current can induce a magnetic field, and we have that circular loop, which again, I'm just so convinced that we're talking about one singular entity, one field that's operating here, but we haven't gotten there yet with our brains in physics. But anyways, that won't help you on this test. So let's get back to this. This guy wants everything to stay the same. So he's going to generate with the current that is generated in him because of this changing magnetic field, he is going to generate a field that is in the same direction as this magnetic field because he wants to make it stronger. So when he does that, this is what this looks like. So you have this loop up here, right? And he has a magnetic field that is coming into the screen. When you're doing this, you're going to use your right hand rule. Okay? And you're going to have your fingers go through the center. Because remember, these are like arrows. That's how we, and you know, when you have an arrow like this, it's because it's coming out of the screen. You're seeing the tip of the arrow. Well, this, he's going to have one going into the screen. So your fingers, when you curl this over this part right here, over the very top of your loop, your fingers are going to go through this, and you have to use your right hand, and then it'll curl up. And yes, you will have the top of your fingers coming out here, but that's fine. It doesn't matter what they're doing after they go through. It only matters what's happening with your fingers through the center of the loop, okay? That's all that matters. And then when you do that, you're going to see that your thumb is pointing to the right. This means so your fingers, as we see here, are the magnetic field with your right hand. Okay? Your thumb, it's a really long thumb. He is your current. So, if this was a clock, you would have, you do a different color here. You would have 12, 1, 2, 3. If you're going this way, to the right, this is clockwise. This happens when you have a positive current, because if your field is decreasing, now it doesn't always mean that you'll go in to the screen, okay? What it means is that if there was originally a magnetic field going into the screen and it was decreasing, this wire is like an old man. He wants everything to stay the same, or he's like a lot of the physics people that don't want to, you know, change their ways and things, right? Or just anybody that doesn't want to change their way. It might even be you. It's been me a few times in my life, right? And he doesn't want to change. He wants everything to stay the same. So he says, I, too, am going to try to stop this weakening by creating a field. I'm going to add to you by creating a field also in the same direction. That just so happens to be to the right here. Now, say that we had a field that was originally coming out at the screen at us, right? And it was decreasing. The wire, too, would create one coming out at us, okay? So if it is, again, coming out at us, then what I would do is I would wrap my fingers over the top of, well, hold on, sorry. If it's coming out, yeah, I would wrap this because I need my fingers to first come out this way, because that's what's happening, right? This is a arrow. I want my fingers coming through the middle. It only matters what's happening through the middle. And when I would do that, my thumb would point to the left. So here, I would be going counterclockwise. So it doesn't always, my current would be, okay? So it doesn't always mean that if something is decreasing, you're going to go clockwise. It just means that if there is a change, the current that is induced is going to oppose that change. So if the B field is getting stronger, it's going to produce an opposing B field with its induced current. And we'll see that in another problem, so I won't talk too much about it here. But that's all you're seeing, is that the induced current will create whatever current or whatever B field is necessary to try to keep things the way they are, to not change. Okay, so now let's look at the next one. So again, if your teacher asked you which way this current was induced, you would say clockwise. Right, here we go, because we're going into the screen. Yes, clockwise, because he would be this way. Oh, where's my pencil? Because he would then be going this way. Okay. All right, here it says, a conducting bar slides without friction on two parallel horizontal rails 50 centimeters apart. The resistance of the bar and the rails is assumed to be constant and equal to 0.1 ohms. A uniform magnetic field is perpendicular, so we have a different thing going on here, to the plane of the rails. A force of 0.08 newtons is required to keep the bar moving at a constant speed of 0.5 meters per second. What is the magnitude of the magnetic field? Okay, so we have a few things going on. So in our given section, let's go ahead and write down a picture as well. So if we have these two conducting bars, right now it's an open loop, right? It's not closed. And in order for you to have a circuit of any kind, it needs to be a closed loop. So what we would have is we have a bar here that is placed of like copper or aluminum, some type of conducting metal, and it is moving, let's say, at a constant velocity of 0.5 meters per second. So we'll have like 0.1 and 0.2. So he's moving from here, just moving along. Okay, so we'll just say position 1, position 2, like we took little snapshots in time. And we know that the distance right here, let's do a different color, that here to here is 50 centimeters, which is 0.5 meters apart. And the resistance of the bar and the rails, so R, let's do a different color, R equals 0.1 ohms. And then we have a uniform magnetic field, which is perpendicular. Perpendicular, we'll look at that. Perpendicular means that it forms a right angle, right? So it's going to be like this. So if I have, we're going to do the same thing. We'll do into the screen. Say I have a B field. I'm going to do a different color. Into the screen, because it doesn't tell us which way, so we could make them, you know, whichever way we want as long as they're perpendicular. So we have a uniform magnetic field, perpendicular. All these kind of big, so we're not drawing X's all day. So B is perpendicular to the plane of the rails. So if we have perpendicular, that means it's forming a right angle, right, with these rails. So it could have been in or out, but we're just going to say in. We'll say B into the screen. And then let's see, what does it say? It doesn't say how much. Oh, that's what we're finding. Okay, so we need to know how much. But we've gone ahead and put that it's into the screen. And then we're given that a force of 0.08 newtons is required to keep the bar moving at a constant speed of 0.5 meters per second. All right, so what don't we know? Well, we don't know the magnitude of the magnetic field. Something else we don't know the current, and that's in a lot of, we don't know if we'll need it yet, but we may. Let's see. Oh, and we put down here length. We already labeled it, but we'll put it as 0.5 meters. Okay. So if we're looking at these things, these right here, the things we're given, what relationships have we learned about so far? Well, we have something about force. How does force relate to a magnetic field? Because why would we be given it if it's not going to be talking about some type of relationship? Well, we know that force created by a B field, right, is ILB. Okay. Well, then we're given here that we're moving at a constant speed. So that means our acceleration equals 0, right? Because if you're accelerating, you don't have a constant velocity. So we know from Newton that the sum of the forces equals mass times acceleration, which we have here is 0. So we could say that our force, because we can say it equals 0, we can have our force equals, what, 0.08 newtons minus ILB equals 0, right? Because technically that's like saying it's the same thing, equals 0. So the sum of these equals 0. Okay, what else do we have here? So again, we're talking about we have resistance, and again, I think we're really going to need I. So we are having a change here. Let's see, what's changing in our relationship? Well, we're moving. So that means that the area, is the area changing? Because it's the area of the plane. It's the plane of the area, right? When we were talking about this equation, whoops, right here. EMF equals negative N delta phi B over delta T. And we know that phi B equals BA cos theta. And we know here, let's go ahead and let's talk about this cos theta. We know that it is perpendicular to the plane of the rail. So since it's perpendicular to the plane, then it's going to look like this. So we have our B, let me get my red back. Here is our magnetic field going this way. And if we look at this guy right here, we'll see if we had a face on him, he would be going out this way. So he is going like that. So this is a 180 because they're in completely opposite directions. And he is flowing through this guy. So it's not like he's like this guy up here who nothing was touching him, right? This is coming straight through. So we have, you know, this guy going into the screen, and then we have the plane of the area. Oops, it's supposed to be blue. Looking out at us. So that's a 180. So if you ever have heard somebody say, man, they did a complete 180, that means they went in a completely opposite direction. So that's how I remember what 180 degrees is. So we know, we can put that in our givens, that our theta equals 180. Okay, and our area here, well, when you're talking about area, you're talking about the plane of the area, which we know this is just a rectangle, right? And the area of a rectangle is length times width. Okay, so if this equation right here, it has a change. So if we write negative N delta, and then we put this in, BA cos theta over delta T. So we put him in just right here. Well, the thing about a change is that if something isn't changing in this, we can pull it out. So what is actually changing? The magnetic field is uniform. It's not changing. So we're not having a change in our magnetic field. So we can pull him outside. So we have B, he's constant. Well, our area here, we said we know that our area is length times width. Okay, is our length changing? Our length here is of our bars. That's not changing, but our width, the width is changing because as it's going from here to here, right, there's a change in width constantly. So we can say that we have BL, but there's going to be a change in this guy. There's going to be a delta W. Okay, so then we have, and our cosine, that's not changing either. If we look at our picture, it's the same amount of area of the plane to the direction of the B field the entire time. So that's not changing. So we have BA, BL, cos theta. Oops, I didn't mean to put a delta right there. It's supposed to be an N. Come on, pen. BL cos theta delta W over change in T. Okay, so we're getting somewhere. But now, how do we know what delta W is? Well, we're given velocity. What is the relationship between velocity and the amount of width that something can change, or the amount of distance? If you remember that distance equals velocity times time. So the rate at which something is moving times the time that it moves will give you the distance that it has moved. So this is our W. It's just the distance, aka the width, that this has moved. So now we can plug in VT for this. So now we're getting somewhere. BL cos theta change in VT over change in T. Well, look, we have 2 times, so we actually didn't even need time. We can cancel that. And now we have negative N BL cos theta of delta V. Okay. So that's the only thing that is changing. Which is not actually the V that was changing, it was the VT that was changing. So we really could even drop that delta now. We don't even need the delta, we can just have times V. Oops, my pen. Okay, so now all of this is equal to the EMF. Okay, well, we have quite a few relationships going on here. So now let's see. What is the magnitude of the magnetic field? Oh, well, look. We could solve for B, right? But before we do that, let's see, because our EMF is equal to I times R. Well, we have I up here. So what if we solve for this in terms of I, and we said force divided by LB equals I. So then we put this in here. You guys, I'm telling you, the more that I do this, the more I am convinced that we are talking about one singular field, because the amount of relationship is just like saying, you know, that this is happening in your heart and then it, you know, affects something somewhere else. Like, I mean, it's just, this is all one entity. Convinced, but I digress. Okay, so we are going to have this goes in for I. So we have EMF equals F divided by L B. Then we can take this, because this would have been IR, equals negative N B L cos theta V. So now for I, we're going to plug this guy in. And we're going to get force divided by LB times R equals negative N BL cos theta V. Now we need to solve for B. So if I want to, let's go ahead and let's multiply this B. So we'll say times B. So now we have negative N B squared L cos theta V over FRLB. And let's also then say, well, we'll do it piece by piece, FRL. All right, and then we will divide away this negative N and this junk to the other side. So we have F R divided by L divided by negative N L cos theta V equals B squared. Okay, so what do we really have? We have F times R divided by negative N L squared, because these guys are both in the denominator, cos theta V equals B squared. So that means that the square root of force times resistance divided by negative N L squared cos theta V equals B squared. It equals B, because we took the square root. Okay, so what does this equal then? Well, you know you can't put, we're talking about magnitude here. You can't put a negative underneath the square root and have it be a real thing. But remember, our N is just 1. There's not like multiple loops or anything. So that's just 1. And then cos of 180 was negative 1. But we're taking the magnitude. Oh, so these would end up being positive anyways, because that would have been a negative and a negative. But let's go ahead and fill this in. So we have our force that we were given was equal to 0.08 times the resistance was 0.1. Is it 0.1? Yeah. Divided by, so that's going to be a positive, a negative 1 times L squared. So where is L squared? L was 0.5. 0.5 squared times, because this would have just been a 1, guys, and that's a 1. And then we have V. V is 0.5. And this is going to give us the magnitude of our B field. So let's put that in our calculator. And I get that the magnitude of our magnetic field is 0.2529822, blah, blah, blah. So we'll just say 2.252 Teslas is the magnitude of our magnetic field. By the way, this is an equation that I would put on your sheet. And you would just have to keep in mind that you would need to take that negative out if necessary to make it work in your calculator. And then I would also make sure that you put in your sheet, you know, that if you don't remember that this equals B, the length times width, that equals change in W. Or length times width, excuse me. You can do change in W equals VT if you don't remember that. But how we just derived all this, this relationship is all explained right here. So somebody took all this business and, you know, I mean, this isn't an equation you're given in class, but since we've already derived it and you understand it, put that on your sheet. And you know, if you're given force, resistance, and length, and, you know, a parallel or a perpendicular, you can plug that in, and a velocity, you can plug that in, and you've got B. All right, so that's exciting too. Let's see. What is, say we wanted to know, because here, are we moving at a different, no, I was going to say what direction is the induced current in, but, well, we could. Let's do that. Okay, so because our magnetic flux is equal to BA cosine of theta, if our A is getting bigger, right, which we said it was because our A was length times width and the width was changing, it was getting bigger, then that means that we're going to have an increasing, because if A goes up phi B goes up. So that means we're going to have an increasing B field. Remember that this guy right here does not want that. He wants for everything to stay the same. So because this is increasing, he is going to create a magnetic field that is in the opposite direction of the current one, because he wants things to slow down. He's like, slow down. So when you're doing this, imagine your fingers are on the top of this, and if you do the top every single time and you're consistent, it'll help. This is coming out of the screen now, so that means you want your fingers, before they do anything else, to come underneath the screen. So your fingers are going to be pointing out this way. And when your fingers are pointing out this way, your thumb is going to go to the left. So this means your induced current is going to be counterclockwise. So if your teacher asks you, okay, well, what is the magnitude of the magnetic field and what is the direction of the induced current, you know always, always, always that when there is a change, which can change with any of these things, it can be the field changing, it can be the angle changing, it can be the area changing, doesn't matter, any change at all, the entity here, this plane, he is going to be looking for a way to make that stop. He does not want the change to happen. So the current that is induced in him is going to oppose this change, whichever way it is. So if it is increasing, if the field is increasing, he's going to try to make it decrease by creating a field that's opposite the direction of the current. If the field is decreasing, he says, oh, no, it must stay the same. So he is going to create a field in the same direction to therefore add to the current magnetic field to try to make it the same. All right, so I hope that was helpful. Whoopsie. Okay. Goodness. All right, so I know that was a long problem, but once you do stuff like that a few times, it won't seem as tedious. Okay. I hope it didn't seem super tedious then. All right. The magnetic field of an EM wave has a peak value of 5 times 10 to the negative 10 Teslas. What is the intensity of the wave? Okay. Now, intensity, just as a reminder, is intensity, which is labeled with I. I don't know. I guess eventually we ran out of letters, but it's not current. This is intensity. Okay, is how much energy a wave can transfer in an area. Okay, so that's the definition of intensity. So now that we know what it is that we're looking for, what that means, let's see what we have here. So we're given that the peak value of this EM wave, so we'll have, is 5 times 10 to the negative 10 Teslas. We know that that is a B wave, EM wave. Okay, what is the intensity? Just going to write out intensity. Well, this is really easily solved with an equation that I'm sure you were given, and it is that intensity equals 1/2 epsilon naught times the speed of light times the peak value of the electric field squared. I should put this as EM wave. Let's put EM wave. Epsilon naught squared. Now this also equals, another way to write this is 1/2 C over mu naught times B squared. Well, we're only given this. So how do we know what we're talking about with this EM wave? Well, we're told that it's in Teslas. And if it's in Teslas, we know that it's the magnetic. So we will just put that, that's sort of like the peak value of B, okay? Or that shouldn't go up there. B naught. Let's see here. Well, we have, well, we know C, that's what, 3 times 10 to the 8 meters per second. And we know epsilon naught is 8.85. These are just constants you should have written down on your equation sheet, or they'll be given to you on a test. And then we know mu naught is 4 pi times 10 to the minus 7. So you could just jump right in and fill this in here. But say for some reason you didn't remember it this way. I want to show you that you could do it another way. So say that you remembered that C equals the peak of the electric field divided by the peak of the magnetic field, okay? You could plug in, because we don't have this one, you could plug in, let's solve that for E. So this would be C, because we need it to be E squared, so it would be C squared times B naught squared equals E naught squared. So you could also take this guy and plug him in right here. And then that would give you an equation of 1/2. It just depends on what you're given. Of C times C squared would be C cubed times B naught squared. So you could also do that, and that would equal I as well. So let's do that. We have 1/2 epsilon naught, 8.85 times 10 to the minus 12 times C cubed, which is 3 times 10 to the 8 meters per second, times our magnetic field, 5 times 10 to the minus 10 Teslas, this is cubed, that's squared. So you could put that in your calculator, and we could also put this one in, which would be 1/2, and then 3 times 10 to the 8 over mu naught, which was 4 pi times 10 to the minus 7 times B squared, oops, not an X. Let's go like that. It's B squared, which again is 5 times 10 to the minus 10 squared. So let's see what these are when we plug them in the calculator, see if we get the same answer. Okay, so for this one, I got 0.000, how many? 1, 2, 3, 4, 2, 9, 8, 4, 1, 5, 5, 2. So interestingly, I got slightly different numbers. I got 0.0002986875, and this would still be to 3 sig figs. We would have, well, it's slightly different, but 2.99, say approximately, times 10 to the negative 4, or you could have, you know, the two. I mean, it's interesting that they're slightly different. But I personally like this one, because when you try to put this guy in the denominator, really practice with your calculator, guys. Really practice, because you'll notice when you get weird numbers. And so I'm going to go with this equation right here. I think this is the best one to have available, because you're not dividing. That just can make things weird in your calculator. Okay, but this is our answer, and we need units. So intensity is energy per time, right? In hours, or in an area. So that's going to be power, which is in watts. And then per area is what? Per meter squared. So watts, you can put that, watts per meter squared, or just W. Okay, so now we're going to jump into, I think the rest of these are from 23, chapter 23. And we only have, well, 4 more. So my teacher really liked chapter 23. Okay. An object is placed 12 centimeters in front of a curved mirror. The magnification of the image is -3. What is the focal length of the mirror? All right, so this can be solved. Let's go ahead and let's just write down our givens. It's always helpful to write down your givens and your unknowns. If your teachers can see that, they usually will give you some extra credit or some partial credit, even if you don't get the answer right. So always a good thing to do. That our object is placed 12 centimeters in front of a curved mirror. So that is called the object distance from the mirror. Okay, 12 centimeters. That's going to be 0.12 meters. Magnification is -3. And what we want to know is the focal length. All right, so if we draw a picture real quick, which we don't even really need to do that for this, but because it doesn't tell us which way it's curved and all that good junk. So let's just use our equations. Okay, so we have a mirror equation that tells us 1 over f equals 1 over do plus 1 over di. Di is image distance, do is object distance. These distances are measured from the center of your mirror, or when we see lenses, from the center of your lens to the object or to the image. Okay, let's see here. We also have our magnification equation, which says negative di over do, which also equals hi over ho, which is the height of the image divided by height of the object. Okay, so we want to know the focal length. So in order to do that, let's solve for di. So we can do that right here because we have do and we have m. So let's solve for di. If we have m equals negative di over do, let's do that in our solve step. We can say m times do, not d theta, do equals negative di. So we have -3 times our object distance of 0.12 meters equals negative di. So that is going to be -3 times 0.12 gives us -0.36. But we have to remember that this is a negative di, so that's going to be times a negative, right? So that's going to be a positive 0.36 equals our image distance. Okay, so now that we have image distance, that was the first thing we did, right? We saw what we had, we saw what we didn't have, and then we put those things together to get what we needed. In other words, we made the relationship work. And then what we're going to do now is solve for focal length, which is what we wanted to begin with, because now we have di and we have do. So let's say 1 over f, this is going to be our final solve step, 1 over f equals 1 over do plus 1 over di. Don't forget to take the inverse of that, and that will make this the focal length, which is actually what we want. Don't get all, now that's another reason why you want to write your work down, because if your teacher sees that you got here and you just didn't inverse your answer, you're definitely going to get some partial credit. All right, so 1 over do we said was 0.12 plus 1 over 0.36 to the -1. Let's see, that is going to be that equals 0.09 meters, or will be 9 centimeters, depending on if they want it how the question gave it to you or if they want it in meters. That is your focal length. Okay, so that's just really about knowing how to manipulate the magnification formula and also the image distance and focal length and all of that good business. Okay, light enters a substance from air at 30 degrees to the normal. It continues through the substance at 23 degrees to the normal. What would be the critical angle for this substance and the air? All right, so critical angle, remember, is the angle where your incidence angle is like just enough to make it to where if you had two substances, say we have a substance here, say this is water and this is air, and say, I don't know, for some reason we have some light coming in from down here in the water, and it's coming in and it's at just the right angle that the light is not going to leave the water. Like, it's just the right angle. So this is when the incidence angle equals barely the amount, which this, if you can see, is sine of 90, is going to be, you know, to where it doesn't enter the other substance at all. It completely internally refracts the light. All right, so this is just a little thought bubble. Matter of fact, I'm going to erase this thought bubble so that way we can see how this applies here. Okay, so we know, like I said, that when theta 1 or theta I, you'll see this as theta 1 or theta I, is at the critical angle, theta C, then we know that our refracted angle is 90 degrees. Now, it's asking us here for the critical angle. So let's see. If we have air, we know that the index of refraction of air is 1. And it continues through a substance. So we don't know N2, right? So we'll call this N1. We don't know the index of refraction of our other material. So let's set this up, because when theta R is 90, so let's use our formula that says N1 sine theta C equals N2 sine of 90. And let's solve for this, because we know N1, and we know that, oh, wait. Okay, so let's not use this one yet. This is going to be one of our equations. We're not going to use it yet, though, because let's draw a picture. We have light entering a substance like this, and it is at 30 degrees to the normal. Remember that all angles are measured from the normal line, which is perpendicular to the surface, whatever the boundary is. So that means that this angle right here is 30 degrees. Now, it's going to bend, because remember, when it goes through a substance, light bends. If it's not in air, it's going to bend because it moves fastest, well, in a vacuum, and then through air. And so it's going to bend. We'll do a sharp bend. Continues through the substance. We still have this normal line at 23 degrees to the normal. So this is 23 degrees. Okay, so we're given this. So when I see this picture, I think, okay, well, I know that this equals 1. N1 equals 1. But I don't know what N2 equals. And so I know that I'm going to have to find N2, because they've given me all of this information, and I know that I have this equation that doesn't change for finding my critical angle. I know that my refraction angle will always be sine of 90 when that happens. So I need to find N2. Well, we have an equation for that, and it comes from Snell's law. So some guy named Snell saw this relationship and expressed it this way. Sine theta 1 equals, or you'll see sine theta I. I'll show you how this can be written both ways. So it could be written that way, N1, or it could be written sine of theta I equals N2 sine theta R. Those would be the equivalent statements. So now if we want to solve for N2 here, let's do it like this. We know N1 sine of our incidence angle is 30 degrees divided by sine of our second one, which is 23 degrees, equals N2. Now, if they ever give you on a test, say this says that the light enters the substance from an air 30 degrees to the water or to a substance. They're tricking you. Because if they give you this and they say that it comes in at 60 degrees to the substance, in order for you to find this guy right here, you're going to say 90 minus 60. Because this right here, remember, is perpendicular to the boundary, and that creates a 90-degree angle. So that's how you would find that if they did give you that and try to trick you. Hopefully they don't, though. But if they do, now you know how to find it. Okay, so N1 we know is 1 times sine 30 over sine of 23. And let's find out what our index of refraction is. That means the ratio of the speed of light to the velocity of the movement of light through that particular material is. Let's see, put that in our calculators. And I get that N2 equals 1.27965. Oh, okay, something's going on here. Hold on. Okay. 652333262. All right, so now we have N2, and we can plug that in right here. Because now we have this, and now we can find the sine of theta c. Okay, so we have N1 is 1, and we don't really need to do anything with that. We can just say that the sine inverse, of N2 sine of 90. Well, I would have to, let's do it symbolically first so it makes more sense. Okay, so if I have this, I would have sine theta c equals N2 sine of 90 divided by N1. So then to get theta c, I would have sine inverse of N2 sine of 90 divided by N1. But even though this is N1, and even though that is how you solve this, this only works if N2 is less than N1. But here we have that N2 is 1.279, right? But we know that N1 is only 1. So even though that this is how the equation is set up, you have to set it up like this. 1 over the 1.27965233262. And then sine of 90 is just out here. He's a multiplier. So it's really N2 over N1 sine of 90, but we had to switch it because N2 must be less than N1. So let's put that in our calculator. And I get, when I put this in my calculator, that the critical angle, goodness, I don't even know what that was. Critical angle equals 51.39 degrees. And say you don't remember that N2 is supposed to be less than N1. It's not really that big of a deal because when you go to put it in your calculator, and if N2 is in fact bigger, or excuse me, N2 must be less than N1. So if N2 is bigger than N1, you're going to get an error in your calculator and it won't work anyways. And so you'll know, oh yeah, I need to switch it. So no worries to be freaked out or anything of not remembering everything. You can always write this too on your equation sheet, and that will help, but you'll get an error in a calculator and that'll prompt you to remember, oh yeah, I just need to switch my N2 and my N1. But your sine of 90 stays as a multiplier. He never becomes a divider. Okay, we're almost there. Now, an object is placed 10 centimeters from a convex lens of focal length 20 centimeters. What is the magnification? All right. So we are given that an object is placed, so that's our DO, 10 centimeters from our lens, which equals 0.1 meters, from a convex lens of focal length, 20 centimeters. We want to know the magnification. We also don't know DI. We know DO, we don't know HI, We don't know HO. We don't know if we need it or not. But our equations, we know 1 over F equals 1 over DO plus 1 over DI. And we know for magnification that negative DI over DO equals HI over HO, which we don't have HI or HO, so that's really not going to be much help. But since we have DO and we have F, we can find DI. So let's find DI. That's our game plan. And then plug DI in. Oh, plug. Goodness. Here we go. Plug DI into M equation to solve for DO. Oh no, to solve for magnification. So that's what we want. All right, so let's do that. So if we have 1 over F minus 1 over DO inverse, that's going to give us DI. So if we go ahead and sub that in, we're going to get 1 over 0.1 minus, I lied, sorry guys, focal length is 20 centimeters, which is going to be 0.2 meters. You could actually probably leave these as centimeters if your teacher lets you. 0.2 meters over 0.1 meters to the negative 1. Let's put that in our calculators. And I got that this was negative 0.2, that's going to be meters, equals DI. So when we go to plug that in here, we're going to have a magnification equals a negative 0.2 meters over object distance, which we said was 0.1 meters. So let's plug that in. And we are going to get that we have a magnification of +2. This magnification being positive, by the way, means that our image is upright. And you'll see also that when we got this negative DI, that negative DI means that it is behind the surface of the lens and that it's virtual. A virtual image is where the light rays don't truly cross. And so if you get a positive DI, you know that you're dealing usually with a real image, meaning that the light rays actually crossed, and then you'll have a negative magnification. And that negative magnification means that your image is upside down. So anytime you have an upside down image, that is going to mean that you have what is called a real image, meaning that the light rays really crossed to actually make that image. Okay, home stretch here. Okay, so this says an object is placed 100 centimeters in front of a lens of focal length 50 centimeters. A lens of focal length 20 centimeters is placed 130 centimeters beyond the first lens. The final image is located where? So for this, we really need a picture. All right, so first let's draw our axis. This is a system of lenses problem. Maybe you've done one in lab, which will really help you with this. So we have here an object is placed 100 centimeters in front of a lens. So let's do our first lens. Whoops. Well, it's supposed to be half. I'm not an artist, so bear with me. It's supposed to be a lens. Remember, we're always measuring from the center of the lens, so I'm always doing that. So we have an object, which is going to be represented by an arrow, and it's placed 100 centimeters in front of a lens. So I'm going to act like this axis here is a ruler, and I highly encourage you to do the same thing because I find that to be super helpful. So I'm going to say that this guy is at 0, and that this guy right here is at 100 centimeters. Okay? And his focal length is 50 centimeters. We're just going to keep it in centimeters because this is all going to be ratios, and ratios are the same no matter what unit you're using. So, and I encourage you to test that too, because once you do it, you'll see that it is, and it'll make sense. It'll be yours, so to speak. Let's see. Then a lens of focal length 20 centimeters is placed 130 centimeters beyond the first. Okay, here's lens 2, and he is 130 centimeters behind this guy. So that means he is from here to here. That's going to be 100 plus 130, which is going to be 230. So he's going to be at 230 centimeters. And he has a focal length of 20 centimeters. Now we want to know where the final image is located. All right, well, if you are, let's go ahead and let's set this up. The way that you do this is you look at just this part first. You act like the other guy isn't even there, and you figure out where the image would be located for the very first part. So that's going to be our game plan. All right, so if we have, let's do, if we have an image right here, it's going to go like this. Well, let's not even do a ray diagram. I don't think we need to. We can say 1 over F equals 1 over DO plus 1 over DI. So we know that DO is 100 centimeters because he's 100 centimeters from the center of the lens. So DO1 equals 100 centimeters. And we know the focal length, so we can find the image distance. So let's do that. Let's solve. Let's say 1 over F minus 1 over DO equals 1 over, well, we'll take the inverse of these, and that'll just make it DI. So we know 1 over 50 minus 1 over 100 to the negative 1 will give us our image distance. So I get that our image distance is a positive 100 centimeters. This is DI, we'll call it DI1. Now, because this is a positive DI, this means it is a real image. Therefore, you know it will be what? Upside down. And it will be on the right-hand side. Right? That is right. This side. Yes. It'll be on the right-hand side of your lens. You can also know this by practicing doing your ray diagrams, which shows when a light ray comes in here. It'll then go through the focal point on the other side, not of the second lens, but lenses have a focal point on each side, and go down. And then you'll also have one that goes directly through the center and then crosses. And where they cross, where these lines converge, these rays converge, you're going to have the bottom of your image right here, which is going to be the top because the rays came from the top of the image. So what they will produce is also the top of the image. And the bottom of the image is always drawn to the axis. So that's another way that you can know. Or you can just remember the sign conventions that if you end up with a mathematically positive DI, this is going to be a real image, and it'll be upside down, and it'll be on the right-hand side of the lens. Also, you can see that he's not just going to be here at 100 centimeters. He's going to be at 100 centimeters past this center of the lens. And because we know he's going to be on the right-hand side, this is going to be 100 plus 100 centimeters. So he is going to be located at 200 centimeters on our axis here. Okay, so now we're done with lens 1. So now we're looking at lens 2. Well, lens 2 only can see what the first lens showed him. So this is going to be DO2. This is going to be the other object, right? So from here to here is going to be our object distance 2, because this is all that lens 2 sees. He doesn't know anything that is going on over here. He only knows what he's told, what he's shown. And so he thinks that this image is the object that he's seeing. And so if we want to know the object distance, all we have to do is say 230 minus 200. And that's going to give us that 30 centimeters equals the object distance from that object to lens 2. All right, well, we want to know where this image is going to be. So this is lens 1. This is going to be lens 2. All right, so if we'll do the same thing here so we can find out where the image will be produced on this side. Well, we know that 1 over f equals 1 over do plus 1 over di, and we have that we have the focal length and we have the object distance, so we can find di. We'll do that by saying 1 over 20 centimeters minus 1 over 30 centimeters to the negative 1, and that'll give us di. So let's put that in our calculators. And I get that our image distance, we'll call it image distance 2 or image distance final even, is 60 centimeters. But remember, he's not at 60 centimeters. He's at 60 centimeters from the center of lens 2. So this is going to be 230 plus 60. So he's going to be at 290. And remember, he's going to be flopped now, right? Now, so that makes him, because he's essentially upside down with respect to the object, right? The image is going to be upside down with respect to the object. So he looks technically right side up, right? But when you're measuring right side up and upside down, you're measuring it in reference to the object. So in reference to this object, this image is upside down compared to that, right? Everything is about perspective. So if we can see that these two are flopped, we can see that this is still a real image. So if your teacher says, well, is your final image a real image? You can tell if it's opposite this one. So if it went from up to down to up, you know that this is a real image. Okay? And now we want to know, where is the final image located? Well, the final image is located where? Remember, you measure them from the center of the lenses, so it's going to be 60 centimeters from lens 2. So we'll say image final is 60 centimeters from lens 2, but from lens 1, we have 290 minus 100 equals 190, so he's 190 centimeters from lens 1. There you go. And that is how you do that problem. So I hope that you found this helpful. I encourage you to write down the sign conventions. There is, in chapter 23, there's 2 sections, especially in the problems, in the books, that go over the sign conventions. If your teacher allows you to write the sign conventions on your note sheet, I would recommend doing that, because if they say, well, is this a real image, or, you know, based on the magnification or based on the orientation of the image, you're going to want to remember those. And if you're allowed to write them down, then absolutely do that, so you don't have to like get to the test part and, you know, wonder if you have forgotten something. So that's good to have written down. But if not, I really hope that this was helpful and a good review. Keep practicing.